In the last video, we learned how to find area under polar curves like exponentials and spirals. We also looked at the flipped case and when there's an intersection in the relevant angles. After that, we learned how to find the area enclosed by sinusoidal circles. In this video, we will learn how to find the area enclosed by cardioids. Then, we will move on to combinations of circles and cardioids. We will use symmetry to simplify these problems, and we will also demonstrate other examples involving symmetry. Before we begin, this is part 3 of the series on finding polar area. If you have not watched the previous 2 parts, I recommend watching those videos first. You can find them in the top right corner of the screen or in the video description below. The first pair of functions will be 2 cardioids. Our goal is to find the area of the purple region. To do that, we first need to know where the 2 curves intersect. Let's create a vector that points to the red cardioid at an angle of 0. As we sweep the vector to the intersection point, it traces out the red region. Once we reach the intersection, the tip of the vector lies on both the red and blue curves. From there, we transfer the tip from the red cardioid to the blue cardioid, then continue sweeping all the way to pi radians. This traces out the remaining part of the target region along the blue cardioid. We know by intuition that the intersection occurs at 0.25 pi, because these are 2 standard cardioids arranged systematically. So to find the red area, we integrate the red cardioid from 0 to 0.25 pi. Expanding the binomial gives us the next expression. Then applying the trigonometric identity for cosine square, we rewrite it in a more useful form. After simplifying, the integral becomes much easier to handle. Integrating term by term gives the antiderivative shown here. When we substitute the limits, we obtain the exact result. We then move the answer beside the corresponding red region. For the blue cardioid, the limits are different. This time, we integrate from 0.25 pi to pi. We begin the same way by expanding the binomial. Next, we apply the trigonometric identity for sine squared. Simplifying the expression gives us a cleaner integral. From there, integration gives us the following antiderivative. Substituting the limits produces the blue area. That result is then shifted beside the relevant blue region. The total area is the sum of the 2 colored regions. Since we already know both parts, we can now combine them directly. Adding the red and the blue areas gives us the exact result that we were looking for. With that, we have solved a fairly complex polar area example. Now, let's bring back the rose curve and use it to introduce a useful strategy for solving questions like this. The area inside the rose is shown here, and this is the region we want to find. In this case, there is an important property that we should take advantage of: symmetry. For example, the curve has this horizontal line of symmetry. We can reflect the shape across the line. There is also a vertical line of symmetry. Reflecting across this line gives another matching part of the curve. But we're not done just yet. There is one more line of symmetry. So we reflect the shape across that line as well. The point of doing all this is to show that we don't need to work with the entire rose curve at once. Instead, we can focus on one small portion at a time. This portion corresponds to the area swept out from 0 to 0.25 pi radians. Those will therefore be the limits of integration. We start by squaring the cosine term. Next, we apply the relevant trigonometric identity. After integrating, we arrive at this expression. Substituting the limits gives us pi by 4. So pi by 4 is the area of this red portion. But remember, the rose is made up of 7 other matching portions with the same area. Therefore, we multiply by 8 to get the total area of the full rose curve. Now, we understand the principle of symmetry. Let's try a harder example that makes use of the same idea. In this case, the blue curve is just our familiar circle. The red curve looks like a cardioid, but it's flipped vertically compared with the one we saw earlier. Our goal is to find the area of the green region. To use symmetry, we can fold the region across its line of symmetry. This means we only need to focus on one side of the diagram. Now let's find the intersection point by setting the two curves equal to each other. Rearranging the equations gives us this form. Then, simplifying further gives us this. So the intersection angle is pi by 6. We can also calculate the corresponding r value, which turns out to be half. Let's mark that intersection point on the graph. Since the shaded region is quite small, let's zoom in a little. First, we sweep along the blue curve from 0 to pi by 6, which is approximately 0.17 pi. This is where the intersection occurs, and the sweep gives us the blue region. Next, we sweep along the red cardioid from pi by 6 to pi by 2, giving us the red region. To find the blue area, we therefore use pi by 6 as the upper limit. The integration steps are already familiar, since we have done similar calculations before many times. The only difference is that the limits have changed. After substituting those limits, we obtain the exact area of the blue region. Let's place that result next to the blue region. Now we integrate along the red cardioid from pi by 6 to pi by 2. This integration is a bit longer than the previous one, but the ideas are the same. We expand the binomial, apply the trigonometric identity, simplify the expression, and then substitute the limits. The exact area of the red region is shown here. So yes, the integration can be a little lengthy, but it's not conceptually too difficult. The harder part is often visualizing how to split the target region correctly. Once that's clear, the calculations become quite manageable. As always, the total area is the sum of the individual parts. We can take both exact results directly from the diagram. Adding them gives us the total area of the target region. Are we done now? Not quite. Remember, we have only calculated the area of one of the two identical parts, so we still need to account for the reflected half across the line of symmetry. That means we multiply our previous result by 2, and now we are truly finished with this example. We now have a strong understanding of how to find area in polar coordinates. Please consider supporting the channel by liking, commenting, and subscribing.